Hello and welcome. This module presents the history of railway signalling from the steam age of the 19th century to the current information age. And we will begin with the steam age before moving into the 20th century and some of the various modernisation initiatives that took place in that century before finishing in today's information age. But to beginning, in the beginning there was nothing that you'd recognise as a railway signalling system. Instead, train movements were authorised and controlled by policemen. A policeman would authorise a train to enter a section of track and then wait a judicious period of time before allowing a subsequent train to enter that section, in a principle that was known as time block operation. The policeman was also responsible for moving points to control train movements at junctions, causing them to take different paths over the junction. However, with the wisdom of many years of hindsight, this method of controlling trains had a number of serious drawbacks. The time block operation doesn't actually guarantee that a train is a safe distance ahead before another train is authorised into the same section. In fact, the first train may have broken down, derailed, or been forced to stop before an obstruction, before the second train is then authorised into the same section and could potentially plough into the back of it. The fact that a policeman had moved points into the required position for trains going over a junction doesn't actually necessarily mean that they stay in that position. They could move underneath the train. And last but by no means least, the policeman is a human being, so could make a mistake. And in the wake of a number of serious accidents, various Acts of Parliament were passed. Particularly important was the Regulation of Railways Act 1889, which mandated the block system, whereby railways are divided into block sections which train cannot be authorised to enter until the previous one has left. Hence, no matter how long a train remains in a section, because it, for example, has broken down or derailed, the second train won't be allowed into that section until the first one has been cleared by whatever means is necessary. It also mandated continuous self-applying brakes for passenger trains. So if a passenger train splits, then the brakes on the train would apply automatically and the carriages wouldn't simply roll away. And finally, it mandated interlocking of points and signals. So the role of the policeman was replaced by a dedicated person known as a signalman, who, instead of procedurally authorising train movements, authorised train movements by devices known as signals, which you see in these semaphore arms on the diagram. And the signaller from the same location also moved points through a series of rods and levers. And the role of the interlocking was to prevent the signaller moving signals and points in any combination of ways that could be unsafe. So, for example, authorising a train to travel over a junction without having moved the points into the position required by that junction. Other legislation introduced something called a facing point lock, which is a mechanical lock that physically holds points in position as a train is authorised to travel over them. So not only does the interlocking prove that the points are in position, it also proves that they are physically locked in position by the facing point locks before trains are allowed to go over them under the authority of a signal. And this prevents the trains moving underneath the points moving underneath the train, and also mitigates the risk of a signaller making a mistake. The 20th century saw various modernisations, particularly around the increased use of electricity, though ultimately the principles that were established in the steam age are still with us today, in spite of the many changes in technology. Initially, electricity was used for communication between signal boxes at either end of block section, So one signaller could communicate to the other that the train had cleared a block section by an electrical bell code, and the signaller at the other end could also tell the signaller that at the far end that a train was coming. But as electricity became a more mature technology during the course of the 20th century, it started to replace other things, including the mechanical semaphore signals, which gave way to electric coloured light signals. And as these were controlled by electric switches rather than mechanical wires, they could be placed a lot further from the control location and a lot further apart, and hence accommodate larger stopping distances. And larger stopping distances then translates into higher speed of operation. So instead of being limited to sort of 60 or 70 miles an hour, we could start operating trains at 100 miles an hour or more. But it's not just the headline maximum speeds that's important. The speed that trains can travel over diverging routes at junctions is also very important. And as electric motors replaced human muscle power as the motive force for moving points at junction, so those points could be made longer with larger radius of curvature on the diverging path, making higher speed diverging routes possible. So trains didn't have to slow down quite so much from the diverging route, and hence that had a significant impact on overall journey time and capacity. We also saw the advent of electricity in train detection. So instead of relying on signallers procedurally confirming whether a block section is clear of trains, this could be done automatically with a device known as a track circuit. Electric relay circuits also automatic commanded points and signal aspects. So instead of a signaller physically moving points and signals, they simply requested routes from one signal to another, and the electric circuits did the rest, commanded the points into the required positions and commanded the signals to display the required aspects. And thanks to this level of automation, an individual signaller could control much larger and more complex areas from a signalling control centre. As the century progressed, so relay-based interlockings ultimately started to give way to more compact computer-based interlockings. And the same thing happened to the electromechanical push-button control systems, which gave way to VDU computer-based control systems that could also even set the routes automatically in accordance with a pre-programmed timetable and algorithms to prioritise certain train services at junctions. Also in the late 20th century, we saw the early introduction of comprehensive automatic train protection systems, which continuously supervised train speed and intervened if the train travelled faster than was authorised or travelled too far, to prevent the driver error leading to an overspeed or train reaching a conflict point with another train. And once you have enough information and computer powering to provide continuous automatic train protection, it's a fairly small step to provide what's known as cab signalling, where instead of authorising trains to move via mechanical or colour light signals on the lineside infrastructure, the authorisations can be presented in the driver's cab, as we see in this display here. There's a number of advantages to doing this. Cab signalling overcomes the spacing and sighting limitations of lineside signalling, and hence can be used to enable trains to travel at higher speeds because you're no longer dependent on drivers being able to see lineside signals, which can be difficult at high speeds. You can optimise the position of signalling block sections to get a higher capacity line, and avoid all the costs associated with constructing and maintaining lineside signals and all their associated equipment. As we move into the information age of the 21st century, we saw standardisation of ATP and cab signalling through the European Train Control System, ETCS, as well as the introduction of radio-based transmission of signalling data, also under ETCS, using radio block centres, and further centralisation of control in railway operating centres. Further extension from ATP to cab signalling is to go as far as actually having the trains drive themselves in what is known as automatic train operation, and this is enabled by the latest ETCS standards. So instead of simply presenting signalling authorisations in the driving cab, as cab signalling does, the trains are driven automatically in accordance with those authorizations, which has some advantages because it enables improved capacity by providing a more consistent driving style with higher braking rates. It can also enable dynamic regulation of speed by a sophisticated control system known as a traffic management system, which can offer some other benefits. Optimization of the capacity at junctions. If you have two trains approaching a junction, you can slow one down and speed one up to allow the traffic flows to move smoothly, rather than forcing one train to come to a standstill and then accelerate over the junction. And similarly with station platforms, if a train's due to arrive at a station platform that's occupied by another train, you can slow it down a bit and avoid the situation whereby the train is forced to wait outside the station platform, which can be frustrating and impede capacity, and also entail wear and tear and unnecessary energy use. And in fact, there's even safety benefits for this type of operation, because you don't cause trains to travel any faster than they really need to, and reduce the frequency with which they come to conflict points. You slow them down long before they get to a conflict point. Actually, some of these benefits don't even need ATO, but could be realised by providing some advisory information in the driver's cab using a concept known as the Conducted Advisory Driver System, or CDAS. So in summary, we saw how some of the key principles of railway signalling that were introduced in the steam age are still fundamental today, those being the block system, continuous self-applying brakes for passenger trains, interlocking of points and signals, and facing point locks. 20th century modernisation introduced electricity to power signals and points, enabling higher speeds, both higher maximum speeds and higher speeds over diverging routes, and also ushered in a trend of ever-increasing level of automisation and centralisation of control thanks to electrical train detection and relay circuitry. Computer-based signalling gradually displaced relay-based signalling, and comprehensive automatic train protection and cab signalling started to be introduced in the latter part of the century, and in the current information age they became standardised through ETCS, European Train Control System, which also brought the advent of radio-based transmission of signalling data and automatic train operation on mainline railways. Thank you for your attention. In the next few modules, we're going to look at some of the key principles of railway signalling, so please do continue.